Now, usually, I give a different talk to geologists, a different talk to the general audience, a different talk to the chemists. They're all interested in some other thing about synthesis of diamonds and how to make them, right? Mineral clubs. And so, didn't know exactly what our audience was. So I stuck a lot of the slides in. And so some of the slides we're going to kind of gloss over, right? Because they probably won't be of interest to non-geology majors as geology majors, like when we're exploring diamonds and stuff like that. How do you explore for them, right? Kind of mildly interesting to you, but maybe not as nice as how do we get those big diamonds and how do they cut them, right? Oh, well, I'll stick a little of that in then. All right? Are we ready to go? All right. Oop, we lost the first slide. Let's try it again. All right? The first slide shows you the most exquisite diamond that we currently have on Earth. It's called the Millennium Star, owned by Nicky Oppenheimer, who happens to be the head of De Beers. Okay? The #1 diamond mining company in the world, by far. And it says natural versus synthetic. So we have to know what the difference between a natural diamond is and a synthetic diamond is. A synthetic diamond, well, let's go back one slide. Okay. Now, I can do anything I want to the exterior of the diamond to enhance it in any way we want, and it's still considered natural. We get to the point where we can change its color by irradiating it and heat treatment, and it's still called a natural diamond, but you're supposed to say it's now enhanced. 3/4 of the people don't say that. Like when you get those nice blue topaz, they've all been enhanced. They've been heat treated and irradiated, and they say, look at this London blue topaz. It didn't come out of the ground that way. It's still a natural diamond. To be synthetic, you have to start off with something that has an atomic arrangement on the inside that's completely different than the name of the mineral, and then you turn it into the mineral that you're interested in, and then you're supposed to say it is synthetic. Synthetic. If we go to the next slide, we can see a couple words that are really important. The first one is mineral, right? And that means it's naturally occurring. All minerals are supposed to be naturally occurring. So diamonds are minerals, and graphite are minerals. And this means they have specific atomic arrangements, and they're all made out of the same thing, carbon, just pure carbon, right? I can burn a diamond, I can burn graphite, we can burn coal, right? But the internal atomic arrangement is much different on the diamond than it is on the graphite. The goal of synthesis, the goal that we want to have, is to be able to turn this stuff, which I got a lot of, and it's not that valuable, into this stuff. And we'll show you how to do that at the very end of the presentation. We've now gotten to the point that we can turn graphite fibers into diamond fibers directly, right? We haven't been able to mass produce this, but we got the technology now. Let's go to the next slide, and we'll see the word mineral again, and we'll see that the definition of minerals, it starts off says naturally occurring. So, if it's naturally occurring, Mother Nature made it. Second thing is it has to be inorganic, solid. So there are a lot of minerals that you buy at the mineral store, at the mineral shows, and you see them that are not true minerals, like amber. It's natural, organic, carbon-rich pine sap, right? So sell it to you as a mineral at the mineral show, but it's not truly a mineral because it's organic, and that's the second word in the definition of a mineral. It's inorganic. Over here, man-made minerals require the synthetic in front. And this is made De Beers, and a lot of the companies really upset. They are afraid that the synthetic world is taking over the natural diamond world, the natural diamonds. So De Beers ran this diamond trading company to run this survey that says 94% of all women prefer real diamonds, trying to stop the synthetic diamond business from making its entrance. Not a chance. The synthetic diamonds are 10% of the cost of real diamonds, right? And they're just as good, even better in some regards. So I've always maintained that it also depends on who made it for you. What woman could resist a diamond made by this guy if he went? Boy, I bet you 100% of the women would prefer one that was made by that guy compared to a mad scientist. I'll show you the next slide. And this is the boring part. This is the phase equilibria, the chemistry of it. And on this axis, we're going to have the temperature. And on this axis going up, we're going to increase pressure. Now, the reason that this is strange is that when I really want to make diamonds, I'm going to make them deep in the earth. So I'm going to go up on this scale. The higher I go up on this scale, the deeper I am in the earth, right? So I'm way down into the mantle. So right here at the bottom of this scale are surface conditions. Relatively cold, relatively low pressure. Now, to make a diamond, I have to be up in this yellow field up there somehow or another. Once it's made, it can continue to exist even down here where graphite is stable, as long as I stay in the hatchet area with the yellow features on it. So I can make a diamond up here, and I can bring it down here, and it's stable. Right? Now, if I want to take graphite and turn it to a diamond, I cannot take it to here, because see this gray hatchet area? That is the area where graphite is stable in the diamond field. So most of the high pressure, high temperature work that I did was right here. I had to start with a diamond seed to make a diamond. We want to get to this field. We can now have the technology to get to this field where I can take graphite, turn it into this field right there, and it'll go directly to a diamond itself. The early high pressure, high temperature machines would only work in this field, and so I couldn't use graphite as the starting material. I had to put in diamond seeds, and then the diamond seeds, I'd take a diamond from here and raise it up to this temperature and pressure, and it would go diamond because it was in the diamond stability field. Now, natural diamonds have a real interesting course to get from here to here. They don't come down through this field here. They actually come through a field that involves going through the liquid and going through the vapor. Right? This is going to cause a huge expansion as this diamond is coming towards the surface of the earth. The pressure, when you take pressure off of a vapor, you get a huge expansion. So when these diamonds are going to get through the surface of the earth, they're going to bust through at a velocity of Mach 5 and a temperature below freezing. We're going to have volcanic eruptions that are so cold. The only people that were interested in this research in the beginning were the military. They wanted to be able to blow up a building at Mach 5 and then be able to go in and read all the papers. Everything was frozen, right? So a lot of the early research of this field in here was was military research. Let's take a look at the next picture. This next one is going to show us a couple ways to get that high pressure. The first way is a meteorite impact. The largest diamonds on Earth are called carbonandos. They are found in impact craters from meteorites. And you can get large masses of them, but the burnt look to them right there is undigested graphite inside them. So nobody was interested in them. Well, I mean, they could grind them up and use them for abrasives, but the diamond industry is not interested in them. We have a fairly large specimens of these inside of the United States at Canyon Diablo in Arizona. Some of the most recent research is really interested in whether these carbonandos were formed by hitting plants and organic vegetation here, and the impact of the heat and everything else turned them to diamond, and they were carbon before, or whether they were part of the incoming meteorite, right? That did not get vaporized because diamond has such a high temperature to vaporize it. More and more research is beginning to show that that's part of the meteorite. And there are lots of nanodiamonds now discovered in meteorites all the time. And a lot of the carbon that might be out there in the universe is actually in the form of diamonds. What is it, Lucy in the sky with diamonds? All those sparkles out there are diamonds. No, you can tell I'm not an astronomer. Next picture, please. Okay. In this diagram, we're going to take a mad scientist right there. And the reason he's got to be mad scientist is because he's going to want to work with organic matter up there. See the organic matter? Right? I am going to either work with organic matter or some form of carbon, maybe graphite, or to turn it into a diamond. My work was what we call HHT, high pressure, high temperature. And we used what we called piston cylinder machines. To create that pressure, I had a big press. This was the GE machine, all right? You'd have a cylinder, and it gets smaller and smaller and smaller on the pistons. And right here, right down inside it, right there, is the sample chamber in red, all right? In there, you're going to have your carbon material. I'm going to turn this carbon material into a diamond, okay? Now, to get the temperatures, I had to have big circular rings of tungsten carbide, shrink-wrapped or shrinked so that they had counter pressure on them, so that when I put pressure on here, the counter pressure would interact, so I could get real high pressures in there. I would run electrical. I'd have a carbon circle inside of there for a furnace, okay, and I'd put a big electrical charge on one side and the other side, and then as they flowed through the carbon, it would heat it up in resistance heating to get exactly the right temperature. We could control the temperature, and we could control the pressure, and we could make things that are equivalent to the mantle of those upper two stars in that previous diagram. The next diagram shows you the easiest way to generate it. Just bury it deep inside of the earth. That's the right picture, number 7. So if I'm deep inside of the earth and the conditions are just right, I'll have a diamond stability field. As we have diamonds, they are not the lava itself. They are picked up as the explosive lava and the vapors come through the diamonds. So the diamonds are just riding along on this volcanic eruption. Here's the volcanic eruption. My research wasn't so much on the diamonds. I was actually working on those lavas. When those lavas hit the surface of the earth, we've already mentioned that they're going to come out with a tremendous velocity of Mach 5, and the temperatures are 32 degrees Fahrenheit. I can tell you about one mistake our lab made. We had these were called bombs, and we had a pressure blowout on one of the bombs, and it broke the seal, came through the cinder block wall on that side of the lab. We had a secretarial pool in the middle. Went through the cinder block wall on that side of the lab, okay? Went right over the secretary's desk. She quit that day, by the way. Ended up in my lab, okay? And when you picked up that container, it was freezing cold. Freezing cold. Because the huge expansion on that gas is like a fire extinguisher going off. When those CO2 fire extinguishers go off, they get really cold. So when this stuff hits the surface of the earth, if you were caught in that lava right there, you'd be frozen to death. You wouldn't burn up. Modern lava flows, you'd be burned to death. There, you'd be frozen to death. Now, if we go down and we take a look at this material, this is called kimberlite. It is where the diamonds are going to reside. So let's take a look and start to go down into this kimberlite pipe. Right? Now, fairly far down, we're going to find Archean rocks. This is telling me it's very early Precambrian rock. The conditions that were allowing the outgas of CO2 only occur in the Precambrian. We made all of these diamonds in the Precambrian. We don't have the same conditions existing today. We don't see these types of eruptions existing today. So they're very old. The diamonds are all very old, unless we synthesize them and make them out of something else. Then they're young diamonds, only a few days old. We'll show you some of those as well. But we explore where we can see this Archean rock on the surface, sometimes covered by other little rocks, but in general, we're going to see Archean again in a little while when it comes time for exploration. All right, let's go to the next slide and drill down and get down deeper and deeper into this kimberlite. Here we are in the kimberlite deposit. This is blue ground because it has a blue color to it. I have a couple of blue ground pieces here with diamonds on them. See that one right there? There's a nice sized diamond in it. All right, here's another one with a little diamond in it here. These don't project as well as you can see them on the screen. All right? And we're pretty far down. This slide shows right here. Here's the blue ground starting right there. This is where the surface waters over years and years have interacted with the blue ground, and they change it to a montmorillonite yellow, all right? And so you have to actually get down into the kimberlite deposit, right? And you can actually see right there where you're beginning to look at it. This is like, I say, finding a needle in a haystack. Most of the people who worked in the diamond business, all the people that they employ, most of them have never seen a diamond in their kimberlite. Somebody finds one, it's really rare. Now, if you really want to find a diamond, you're going to want nature to process it and concentrate it for you. So we'll go to the next slide, and that slide shows you how nature can concentrate these diamonds for us. Diamond mining, the pipe itself, but if I let water concentrate it for me, there are a couple characteristics of diamond that allow it to be concentrated. First of all, it has a real high hardness, so it doesn't get scratched very much. So as it goes down inside of water, it rubs up against all the other minerals and destroys them, but it doesn't get destroyed, right? It's got such a high hardness. It also has a very high density for most minerals. So when I get to places where the water slows down a little bit, the diamonds come out and settle with the larger gravels. And we actually, when we talk about slide 11, we can see them mining the gravels. Here is a gravel deposit just downstream from a diamond pipe. They're digging out in this big gravel deposit all the way down to the ground in these potholes. And then they actually pan for them, just like panning for gold. And here is the gravel, and right there, see, there's one diamond right there, and I think there's a second diamond in that picture someplace. But can you see the diamond? Huh? They are actually the same size as the gravel. Huh? You can see the other one too? Okay. There's the other one. Okay. Now, let's take a look at alluvial diamonds. Some places we've never found the pipes themselves, right? And if we go to Brazil, these are alluvial diamonds on all the tributaries of the Amazon and other river systems, and these are alluvial deposits. The pipes have virtually remained undiscovered because of the rainforest. Huge canopies, huge undergrowth, horizons that are 40 feet thick of just litter, all right? And you can't find the pipes. Now, the easiest way to separate them is not to pan them. We do that with we now use some level mechanism, and we run them through an X machine, and when you X-ray the gravels, diamonds will fluoresce in blue, natural diamonds. So you turn off all the lights, run them under the X-ray machine, and pick up the ones that are fluorescing in blue. And those are your diamonds. Much quicker, much easier, and much more dense than the first pictures we showed you. Let's go to the next slide, and we're going to talk about two types of flat surfaces that diamonds make. The first type of flat surface that we're going to use for cutting, references for cutting the diamond, are crystal faces. And we get real crystals directly in the kimberlite deposit. That's a real crystal face there. That's a real crystal face here. The second way, which we often see in the alluvial diamonds, is as they bang into each other, they split along weak bonds. That flat break is called a cleavage. And so I can get cleavage fragments of diamonds. The cleavage fragment, there's a cleavage right there. And when I make a cleavage fragment of diamonds, it will have what they call octahedral cleavage. It'll have four faces coming to a point here, and then four faces to the point at the bottom. And that's a cleavage fragment of a diamond. Much cleaner than the crystal. Remember, that crystal was pulled through a vapor field. As that crystal went through the vapor field, it began to lose some of the carbon off the face. So real natural diamonds will have etching on their faces. Cleavage fragments will be nice and smooth and no etching on the faces. The next picture will show us that much better. Okay? Now, if I have a cube, how can it break to form an octahedron? So I'm going to break this corner off. Here's my cube in red. I'm going to break that corner off in yellow. Right? I'm going to break that corner off in yellow. I'm going to break that corner off in yellow. And if I go around a cube, I have four corners on the top, four corners on the bottom. And I break them off into each one of these corners. If I magnify those, I'll produce the octahedron. These, when you actually look at a diamond deposit and somebody's showing your diamonds, you can tell if they're alluvial deposit. Everything had octahedral cleavage. This is an alluvial diamond deposit right here. They weren't mining out of the kimberlite. That's an alluvial diamond deposit. So, it says start with the red cube, break off each corner in yellow. You end up with the solid yellow octahedral fragment. Show this picture. The next picture is where I bought my first 8 diamonds. Right here. I got 8 of these diamonds to show you. And I bought them because of their very last thing. It says that most diamonds, 80% of diamonds, are used because of their hardness to make drill bits. And my first 8 purchases of diamonds are these 8 right here. Let's show them to you. I'll stick it right there and let the camera point at this. And we're going to pass this around. And they were 2 carats each, for 8 carats. And there's 8 of them in there. Looking at, okay, and this is a drill bit in which I'm drilling down and I'm taking cores of granite out of a big batholith. And that diamond will cut through that stuff, and it's right. And now this one is pretty well shot. There's only about 1/4 of a carat each left. And so we'll pass this around, and you get to see your first 8 diamonds that I bought from this company in the form of a drill bit. Right? So you're, what? You did? Okay. But, so most people are saying, oh, you're going to show us a whole lot of diamonds, and they're so disappointed that the first 8 are all buried inside of tungsten carbide inserts, right? Inside a high mineral. But let's go on to the next one. The natural shape of diamonds. This is going to allow us to know how to cut a diamond. If I can figure out the shape of my diamond, then I know how to cut it. So the first thing is a cube, right? Diamonds can grow into, this will produce square sides and 6 of them. The second one is an octahedron that matches the octahedron of the cleavage, right? It is going to produce 1, 2, 3, 4 triangles coming to a point on this side, and then there'll be 4 triangles coming to the point on the other side, right? There's 4 triangles coming to each point. The next one is called a dodecahedron. A dodecahedron. And in the dodecahedron, it has 12 sides. Now, it's going to have 4 sides, 1, 2, 3, 4 diamonds coming to a point at the top. Can you see the 4 diamonds coming to a point at the top? And then it's going to have 1, 2, 3, 4 diamonds coming to a point at the bottom. And then it's going to have a skirt of diamonds. 1 diamond in the front, 1 diamond on the side, 1 diamond. So it's going to have a belt of diamonds around that way, diamond shapes. 4 diamond shapes coming to a point at the bottom. Point at the top. 4 diamond shapes coming to a point at the bottom. That's called a dodecahedron. Now, in 1916, Golds made 500 drawings of diamonds. And you can get them all. They're all right here. We aren't going to go there. We don't have enough time today. But I've put a few of them on the next slide. So here are a few of Goldschmidt's drawings. And look, here is a natural diamond, and it etched on the way to the face. It's going to have a characteristic etch on the octahedral face. Here is a cleavage fragment of a diamond, right? Nice, smooth surfaces, right? As they come to the surface, if you do all the analysis, he was the first one to record all the shapes of all the diamonds. And there are millions of shapes, it looks like, right? Not quite, but all sorts of combinations. The next one shows you a couple of the shapes we want you to know. The most famous of all the cube shapes comes out of the Congo mines, right? And they see how they on the surface. Then they twin. A twin is one shape of the same shape, tilted 45 degrees, and growing inside of the other shape. Sometimes, as the diamond's growing, it adds to one crystal. Other times, it adds to the other crystal. And that's called a twin. Twin. And so, here's a cube on rotated 45 degrees inside of this one at 45 degrees. And since they're identical, we call them twins. Identical twins, right? So, not only can they grow different shapes, but they can twin. Let me show you a couple of the others. Multiple shapes on one crystal. Let's go to 19. Look at this. I'm going to have my square face right there. Then I'm going to have my belt of 4. 1, 2, 3, 4. The 4 going to a point. So those are my dodecahedral faces right there. There's going to be 12 of those. 1, skirt 2. Here's a cube face. There's a cube face. Here is my triangle of my octahedron face. 1, 2. See them? There's going to be 4 coming to the top. So I don't have to have the pure form every time. I can mix them all up, right? But each one has a different way that it etches. Let's show you the next picture. This shows you a dodecahedral plus a cube, and here's the dodecahedral. The cube cuts off the point on my diamond. Here's the triangle for the octahedron. Here's the flat surface right there in the square for the cube. Look, even when it starts to get distorted, I can tell where I am in the diamond. I can tell whether I'm on the one of the sixes of the cube, whether I'm on the octahedron, right? Now, here's how they etch differently, is shown in the next slide. The etching. This one forms nice pits. In 1916, the diamond was often shown with those little pits. If I'm on the dodecahedron, etch in lines going across the dodecahedron. If I'm on the octahedron, which is right there, there's the triangular face, I make triangular little pits. When it comes time to cut a diamond, you have to know exactly where you are. This one? This one across here? The pits right there? Oh, they're like, they're microscopic. In fact, this is 1/4 of an inch across. Let's show you the next slide. Okay? Use markings to identify. See those lines? Those are the dodecahedrons. 1, 2, 3, 4 coming up to a potential point here. There's the skirt. 1, 2, 3, 4 on the skirt. And then there's before going to the back point. Can you see the dodecahedron? Let's try the next one. Now, 20% of all mined diamonds are cut into gems. The rest are used in industry. Of the mined minerals that are cut into gems, very few of them are retained in their original crystal shape. This is a rarity. This one is 1/4 of an inch across, costs $450. If you go to this site, he'll sell them. The cost of each of these real small, they're called micro mounts. And they'll run anywhere up to $1,000 for just to be able to see crystallographic shapes of real diamonds. Most people aren't interested in the crystallographic shapes of anything, right? If we're interested in diamonds, we want to cut it. And then we want it to look really nice. So let's go and figure out how we cut it, right? In a drill head? No, you orient that diamond because you want the octahedral face, because the octahedral face is harder than any of the other faces. The octahedral face is the hardest face, the 1-1. Okay? Now, the largest uncut diamond in the world was given to the Smithsonian by the Oppenheimer family for the guy who started De Beers, and it's only 1 inch across. That's the largest diamond crystal in the world. Why? Everything else has been cut. Anytime you get a large one, you cut it. It's worth 5 times more. So nobody wants to part with all that money. So all the big ones are cut. If we go to the next picture, right, we can see this. Here in Paris, the largest diamond collection ever. He had 8,000 total diamonds. Of those 8,000 total diamonds, only 16 of them were real crystals. When you go to the Aurora collection, which is the largest collection of fancies right now in the world, they don't have a single diamond crystal in that collection. The person who's assembled the largest diamond crystals all by themselves is Paul Thiel, and in 1982, he had the largest, and he had several diamond crystals when there are millions of diamonds out there. Well, diamond crystals aren't worth much, but we need them. We need to know a little about them to know how to cut the real crystals. So let's go and start cutting some diamonds. A cut diamond increases its value by over 5 times. Here was the Lesotho, okay, right? It's called the Lesotho Promise. The name, when you find the diamond, gets one name. Once you cut it into a gemstone, it gets a different name, right? So there it is. It was bought for $12 million, right? That's what they cut it into. right? That sold for 60 million, right? So if you have one of those big ones, you aren't going to resist that increase in value. So there are no large ones left. Well, not quite. We'll show you a large one in a minute. Okay, let's go to the next slide. Now, diamonds are the most valued commodity on Earth in terms of dollars per weight, right? The Hancock Red recently sold for $1 million, and it was 0.95 carats. If you actually calculate this out, it comes to $14.5 million per ounce. $14.5 million per ounce. Gold selling at $1,000 per ounce is nothing. People say, I'd like to have a safety deposit box that I didn't know about that my great-grandmother left me, and I hope to pull it open and it's filled with gold. You're going to be better off if you pull it open and it's empty except for 3-carat diamonds in the corner. It'll be worth all the gold in the room, right? Right? So diamonds, I can increase. Diamonds are 200,000 times greater than the equal weight of gold. People don't realize it, right? How valuable diamonds are per weight. Now, a proper cut causes a big increase. One of the reasons it causes an increase is because I get to begin to see color. Actual diamonds, when you first cut them, don't show you color. They have to be cut to show the color. Diamonds have high dispersion, which means that the red light, when it goes in, gets bent much more than the blue light. I put this in as a joke. This was in a physics book. They showed it backwards. They showed the blue light getting cut, bent more, right? Here's the way it really happens. The red light gets cut more. Then when you cut the back properly, no light leaks out the back. It makes the light traverse further and further and further around inside of the stone so that when it comes out, you see color. When the diamond is properly cut, you're going to see every color of the rainbow. That every color that you see, every blue, yellow, green, means the light has gone in, moved around inside, then come out. So the sparkle, the colored sparkles of a diamond, if they're cut right, really increase their value. I get all the colored light from internal dispersion and reflection. Let's go to the next one and talk about some superlatives. The Cullinan diamond was the largest diamond ever found. It's the world's largest uncut diamond, found in 1905. It weighed 1.5 pounds. Talking about carats, 3,000 carats. Now, I don't have a picture of it. I have a picture of the first 9 largest fragments out of 105 pieces that were made out of that. Okay, here are the 9 largest fragments, and they've been cleaved. I had to find that cleavage direction and cleave it. Each of those are cleaved pieces. This one, the largest one right here, became that, which was the largest diamond on Earth until 1997. It is still one of the finest diamonds with the best dispersion, and it's in the British Royal Scepter in the Tower of London, right? And it is still considered the finest diamond in the world. Since we're talking about superlatives, we might as well talk about, well, there's one thing here it says. It says right here that this diamond is in fact only a cleave section of a larger octahedral diamond, in which they could tell by the etching on the faces of one apart that it was a piece of a large octahedral diamond. And here it is. This is the large octahedral diamond that they never found. This isn't quite right, which has never been found. We found it last year. We went and found it. And this weighs 3.2 pounds. We're going to unveil it at the news conference later today. But we want to, a lot of people in the front row are like, oh, come on, give me a break. This isn't really. Let's show you the next step. We're going to let you test it. Okay? Let's go to the next slide. Here's how you test. When they break, or faces have, since the internal atomic range, they have what we call the law of constancy of interface angles. A lot of people say, that's got to be a quartz crystal. If it's a quartz crystal, I'll put this little thing right here called a goniometer. I'll put one angle on one face right there. I'll put the other angle on a face like that. And if it reads 46 degrees, it's going to be off quartz pyramids, right? If it reads 70.5 degrees, it's a diamond, right? That 70.5 degree is the diamond octahedron. So here's how you do it. You get the two faces, you hold it, makes a line. Where two faces intersect, there's a line right there. You get that line absolutely horizontal. You take this and you make it absolutely vertical. You put the black edge down on one side, and then you slide it right to the center, and you put the plastic edge down on the other side, and then you read what angle is that, and find out if it's 70.5. If it's 70.5, we are going to call the press right after we're done and have them come and take a look at this, right? Otherwise, if it's 40 degrees, it's a fake, right? Let's go to the next slide.
What do you use to cut a diamond?
What do you use to cut diamonds? We'll talk about that in just a second. We're almost there. The Star of Africa was the best diamond and the greatest diamond for almost 100 years. The current leader of the biggest diamond in the world is one of the ugliest diamonds we've ever seen. And it's called the Golden Jubilee. At 546 carats, it beats out the Star of Africa by about 12 carats. This is now the original thing, what's called the unnamed brown. It was cut in 1997. It was used in coronation in Thailand. At the time, Thailand was under lots of economic stress, so the leaders lied to all the people in Thailand and told them it was just a golden topaz. And so far, most people in Thailand still believe it's a golden topaz, right? But it is the largest diamond in the world. The Golden Jubilee. The ugly Golden Jubilee. Let's go to the next slide, and we'll need to start cutting a diamond. All right? I want to cut this one. This is the most expensive diamond in the world. It's at $165,000 per carat was the one that was sold. This one by De Beers, which we talked about earlier, the Millennium Star at 203 carats, okay, before and after, all right, is valued at $100 million. Let's take a look at the next slide. We're talking about, I always think in superlatives. We've been actually, you can see the Millennium Star. It's been on display since the summer of 2003 in the Smithsonian, right? That's the most valuable diamond in the world. Let's go ahead and go to 34. We want to start talking about cutting the diamonds. I'm going to use the octahedral cleavage as the first step in a cut. And the reason is it doesn't destroy any of the diamond at all. It's going to be on an atomic plane. It's going to break it right through it. Half the diamond, portion of the diamond is going to be there, and nothing's destroyed. So I have to take this rough diamond. I map it to figure out where I'm going to put the cleavages through. Then I put a little laser cut right here to make an indentation. I put a cleaving instrument here, and I hit it. And if I got it lined up right, it breaks right along that octahedral cleavage. If I got it lined up wrong and I mapped it wrong, I shatter it, and it's worthless. So you have to be very careful about how you map that diamond before you start making the cuts. Let's take a look at the next slide. Finding the octahedral cleavage. There's an octahedral cleavage. That means the next cut's going to be at 70.5 degrees. 70.5 degrees. And what I'm going to do is there's an inclusion there, there's a gnat there, there's a peak there, there's another inclusion there. I'm going to set it up so my 70.5 degrees is going to give me the heart right there for the biggest diamond first. And I'm going to figure out where that 70.5 degrees is because of the law of constancy at internal angles, right? And then unpack it, map it, break it, and I'll have two pieces. We showed you how the original Star of Africa was broken into 9 pieces, right? The Cullinan diamond was broken into 9 pieces. All of them were cleaved. It takes years to map a big diamond. You map all breaks before you do them. You figure out you're going to break this one, break this one, break this one, break this one, and then, so it's cleavage in the initial sets of breaks. Now, how am I going to pick out the 70 degrees? That's on the next slide when we start picking out the 70 degrees. The first thing is that I get inclusions called peaks, right? Just like peekaboo, right? Spelled a little differently. And these can be carbon inclusions. Here is a graphite inclusion right there. right? And these occur on cleavage chains for the most part. When I see the inclusions, they will be concentrated on cleavage planes. The next type of inclusion, okay, is, next slide, okay, carbon peaks, inclusions, you don't have them in your real diamond. So if you got them in your real diamond, they'll use a laser, and they'll come down, and they'll vaporize the carbon, or they'll put a laser hole. This laser was probably was pulsing at about billion cycles per second, okay? Because that causes feathering. They're now having lasers that pulse, femtolasers that pulse at 10 to the 15th cycles per second, and they cut real clean holes, right? Real clean holes. And then you can fill them, right, and make them disappear. So you can burn out your gnats, your graphite gnats. Let's go to the next one. Femtolasers? Okay, I don't know what kind they're using now. I really don't. I haven't been in that field for a while. All of these inclusions we're going to take from the American Gemological Society, AGS. They have a huge website in which they show you all the inclusions. They have by far the best photograph of inclusions and how to use them of anybody. And so if you want the PowerPoint, I'll give it to you, right? Because all of these connecting links that are in there allow you to get to some gorgeous pictures. And they're all reproduced with their permission, right? You have to get their permission. Let's go to the next picture. And there's no problem. Feathered inclusions. These are partial octahedral cleavages around a stress point. Can you see the octahedral cleavage developing right there? 70, 70, 70. Right? Okay? Now, those little triangles. Those are called feather inclusions. Here's a garnet. It produces a stress point. It's an inclusion. And this right there is a feather inclusion. Now, a lot of these times, the cleavage plane itself, if I can trap any gases on there, will produce what we call rainbow inclusions inside of the diamond. But they are showing me the octahedral directions inside of my diamond. Those, when you're going to map how to cut that diamond, you look through there and you look for those things. That's what's telling you the crystallographic orientation. Let's go to the next slide. Now, where two faces come together, we made a straight line. Remember, we said hold that straight line parallel to measure the angle? Well, inside of there, we can have what we call tube inclusions that grow right along that straight line. Those are called tube inclusions. When you see them, look, it goes up, 70 degrees later, it goes down, 70 degrees later. See, it's following the faces of the octahedron. Those are called tube inclusions, so I can use those to figure out where I am. Let's go to the next one. This is what I worked on. I worked on the chrome dioxide, the pyrobe garnets, the grosflorite garnets. Those are all crystal inclusions on the inside. They would produce stress points, which would allow me to see the octahedral cleavage. I wasn't cutting diamonds. I was actually growing the other minerals. Let's try to go down to 43. Right? These are twinning lists. Now, as we start to make synthetic diamonds, and we cut them on those octahedral cleavages, and we end up with cut stones. Right now, the two sides, the synthetic side and the natural side, have agreed that they're going to put on inscriptions. Right? They're going to laser cut right on the girdle of the diamond, and they're going to give it a serial number, and if it starts with AD, that means Apollo diamond. That means it was synthetically grown. If it starts with the AGSU and all those others, they're going to look, and that means that they are going to be natural diamonds. So you actually have to know the codes on those diamonds. You can read them right around on the girdle, and that's going to tell you whether your diamond's real or synthetic, right? As long as everybody's living according to the rules. And, of course, we'll find a lot of people don't. Let's talk a little bit about colors in diamonds. Yellow is the most common color. All right, and it's minute inclusions of nitrogen. All right, if we go to boron, it creates a blue color in diamonds. If you have missing carbon atoms, these are called defects, you turn a diamond pink. Right? If you have artificially caused the lattice defects by irradiating the diamond, you turn it green. If you do this really a lot, turn it black. Most black diamonds are really dark, dark green. Right? So I can get all sorts of colors in diamonds. It used to be that colorless diamonds were the most valuable. But marketing has made it so that what we call the fancy have become more and more valuable. Let's take a look at natural red and pink diamonds. Right now, they are the most valuable diamonds. Most of those are coming out of the Argyle mine in Australia, and these are the perfect pink diamonds. Interesting story about these diamonds that almost everything that came out of Australia was yellow and brown, and they were used for industry. The industry doesn't pay you a whole lot for those grinding materials. So Australia went on a huge marketing campaign and said, these are champagne diamonds. These are chocolate diamonds. And the world bought it. The world bought it. And now you buy cognac diamonds from Australia, chocolate diamonds from Australia, and you pay an arm and a leg for a diamond that was worth 1% of what it was 5 years ago, before the marketing campaign. Diamonds are just the heartthrob. There's an emotional aspect to diamonds that's huge. Okay, let's talk about some synthetic diamonds. When we're going to make diamonds, I'm going to make them two ways. First, my way, with high pressure, high temperature diamonds. Largest one we had made at that time was 6 carats. It had to have an enormous amount of energy put into it. Right? Now, the new way of making diamonds. This high pressure, high temperature diamonds are still made. They're going to make the colored diamonds, the blues, the yellows, the greens, right? And they're made in Sarasota, Florida. The company that's making high pressure, high temperature diamonds, big ones, for the jewelry business is called Genesis. From the word Genesis, just to help pull the N, put in an M. Clever, right? Genesis. Now, chemical vapor deposit diamonds, which is what we're going to talk about next, these have a rate of millimeters per day, and I grind down an octahedron until I got this square cube face on the top. I put this in. It's a little button size, about the size of a shirt button. And then I grow the diamond on top of that face right there. And it grows. We can get now to about 4 millimeters a day. That's what we were talking about earlier. Okay? And it just grows and deposits. This makes colorless diamonds. And this is run by the Apollo Corporation up in Massachusetts. They're making all the engagement rings right now. These are making all the fancies. How do we stand on time? Where are we at? Oh, 11 minutes. Maybe we'll talk a little bit about exploration then, all right, before we go back. Let's go to the next slide. Let's see what we got for the next one. Oh, well, let's tell you about the synthetic one. Here's the chemical vapor. What I'm going to do is I take all of those seeds and I place them in there, all right? I place all the seeds in there, and I'm going to grow diamond on top. Instead of going to high pressure, I go the other direction. Actually make it a vacuum chamber, right? And then I flood that vacuum chamber with methane gas. It has carbon in it. I'm going to break the carbon bond between the carbon and the hydrogen and the methane gas. And then I'm going to heat the substrate down here, and I'm going to deposit the carbon atoms directly on the diamond. We'll blow this diagram up in just a second. And then the seed crystals begin to grow. But they're going to grow graphite and diamond both. But let's go to the next slide, which is a blow up of this right here. But the hydrogen down here, I run an electrical arc through there. I break the hydrogen down till where it's a free radical. And then the hydrogen wants to grab something. And it'll come down and it'll grab the graphite and pull the graphite off the growing diamond. It won't pull when I make a diamond atom on my diamond. It's stable. When I make a graphite diamond on top of that growing diamond, the hydrogen comes along and strips the graphite off. So I'm putting them both down, I'm stripping the graphite, and only diamond is beginning to grow on the substrate. The diamond will grow out over the substrate, across here, across my seeds, and I'll get an entire diamond layer across there. some of the applications are amazing. Diamond will conduct heat away from something 200 times faster than pure copper. Diamond has a huge thermal conductivity. In fact, when we start talking about exploration, we often hear this phrase that diamond is called ice. And the reason is if you think you found a diamond, you put it on your lip, and it feels just like a piece of ice on your lip. It's a diamond. It's conducting the heat away from your lip at the speed that ice does, and it feels like ice. But if it's a piece of quartz, you can put that piece of quartz on your lip. Everybody's found out that this is quartz by now. All right? You put this piece of quartz on your lip, and it stays hot. All right? So, all right? Yeah, all right? So, we now are subcoating all sorts of things because, like if this was a gold substrate, gold conducts electricity really fast. But the trouble is I can't put a whole lot of stuff through because gold has a low melting point and it'll melt. But if I put a substrate of diamond on each side to suck the heat away, we can now make that gold go through there really fast. The electricity goes through gold really fast. It won't heat up. The diamond sucks all the heat away. So most big electrical circuits and everything else is going to be these chemically deposited diamond substrates, right? On all sorts of things.
I wonder what would happen if instead of gold, these graphite as a substrate wafer.
As a wafer? Well, actually, running electrical currents through graphite doesn't move nearly as fast as electrical currents running through gold. Yeah, gold can handle much better electrical currents. Let's try the next one. Now, how do I tell a CV chemically vapor deposited diamond from a real one? When I fluoresce these chemically vapor deposited diamonds, they fluoresce in orange to red. Remember, natural diamonds fluoresce in blue. The next thing is that a natural diamond on the way to the surface has to come out of that diamond field way up there where the two stars were, and then it has to come down all the way to the surface of the earth. As it does that, it gets strained. The strain pattern will show up when we fluoresce it as kind of a weave inside there. Natural diamonds have this strain pattern, whereas CVD diamonds, chemically vapor deposit diamonds, are strain-free. There are actually less strains in the new ones that we're making than the real ones, right? See the weave in there? Natural diamond. Fluorescing? Blue. Okay? Now, the future. Let's go to the future here. We want to turn carbon directly into nanotube carbons directly into diamond tubes. Now, this means that I have to get directly into the diamond field. I can't go up to where I was before and hold it there in the diamond field if it's still metastable for my graphite. I have to get to higher things. So here's the next slide, which is potentially the last slide, if we don't do any exploration, is how I'm going to do it. It is called zeta pinch, Z-pinch. Z-pinch was when you have plasma and you run an electrical current through the plasma in fusion reactors and things like that they're working on in fusion research, the entire plasma will compress onto itself. So here's my graphite. I'm going to run an electrical current through that graphite. It's going to make a magnetic field. That magnetic field, if there's a plasma around, will crunch and it'll make its own pressure. So a 10,000 amp current, a heat of 0.001 down a graphite furnace, will it do it? Here are all the calculations. And the guy on the website said, no problem. I know how to demonstrate this method of diamond synthesis on carbon fibers to turn directly to diamond fibers. We are going to pretty soon be able to make huge diamond fiber by Z-pinch technology. That's the future. Next slide says, when they make all these calculations, they use the calculator, and it says, I'm afraid the numbers don't lie, Norton. We're definitely nerds. But since they are modern diamond scientists, he may say back, that may be true, Henry, but we are rich. All right? We are rich. All right. Let's go to the next slide. Right? And we'll talk for 4 minutes on exploring for diamonds. North America. Let's talk about where can you get diamonds in North America. People say, where can I get diamonds? And I say, in your dreams and at the jewelry store, but it's not worth it. Okay? Right? So don't get diamonds this way. You'll never get diamonds this way. But the number one diamond locality that's open to the public where you can actually find diamonds is in Murphyboro. It's a kimberlite pipe. It's made into a state park. They go down and they plow the entire field down here at the bottom. It's like 7 acres of diamonds. It's right in the kimberlite. And you pay a little fee. You go out. They plow it. You have to go out after rain. You can go around. They find them right there on the tops of the rows. 1 person out of every 1,000 finds a diamond. 1 person out of every 1,000. You feel lucky? Go to the park. Pay the fee. These are the diamonds. Hillary has a huge diamond. The largest diamond ever found here has been turned into a ring. It was given to Hillary because this is in Arkansas, and they were an Arkansas family, right? And she still wears that large yellow diamond. Now, prospecting, Archean Age rocks. The first thing you have to look for. These are the outcrops of Archean Age rocks. There's the Slave Province. Right there is what is called the Wyoming Province. If I strip all the soil off, these are where the Archean rocks are. These are the names of them. But right there are more than 400 kimberlites in Montana, Colorado region that have not been completely explored. Over 400. Let's go to 57. Over 400 unexplored Wyoming kimberlites. The first step finding a diamond is to look for it from aerial photo. Go to Google Earth. And you see these a set of linear lakes that have no drainage. Linear lakes that have no drainage. All right? You actually get down onto these lakes, and they'll have discoloration around them. The next thing shows that you take a little acid, next slide. As you come up, you're going to find a discoloration around the lake. You walk on this side, and you drop a little bit of dilute acid, and the ground will fizz. So much carbon and carbonate. You go onto this side of the coloration zone, and you drop a little acid, and it won't fizz. You are entering a diamond pipe right there, right? You want to find a road cut or something, you want all of that brecciated explosion material. It's even nice if it's blue. All right, let's go to the next picture. We still got a minute it's in. Then you go to the ant hill. The ants will dig stuff up. And if you start to find these other minerals like this olivine, this garnet, this chrome diopside, they're all misnamed. Diopside's a pyroxene, but they call those Cape Emeralds. They're green. They're all misnamed. The garnets are red, but they call them Cape Rubies. They aren't rubies at all. They're just garnets. But you start finding these minerals in the ant hills. Those tell you that you have mantle material, especially the chrome diopside, right? If you've got mantle material, you've blown through. It doesn't mean that you have diamonds. Let's show you, try that one. 60? Yeah, let's try 60. Because we're out of time. Diamond called ice, right? 200 times greater than copper. Put it on your thing. You can actually buy one of these for about $100, $90, right? And you can put it right on there, and it tells you the conductivity right away, instantly, right? And it'll tell you diamond, just like that. So you can put up a little money. Take a quartz crystal with you. Why? The diamond will scratch the quartz crystal real easy, and these are cheap, all right? All right? So, okay? The other thing is that you want a grease board. Diamonds hate water. They have an aversion to water. So if you put the diamonds and the material on a grease board that has a little slope with it, all the quartz will get in the water and run down. All the diamonds, water will go around them. They'll repel because of their surface tension of things, and they'll stick to the grease. And you will wash it all down. You have a little grease, just a little butter will do the job. On a little slope, on anything, on a board, you put butter on the board, you put all of the little ground up stuff, it runs down, and the little sparkles right there will likely diamonds. Little interesting facts about how to explore. It's a good place for us to stop. I'll entertain any questions if you have any. Yes. Uh-huh.
How large was that?
The Hope diamond was what, 135 carats, as I remember. It's what it is a blue diamond. Okay, it's one of the largest blue diamonds. The diamonds that have distinct colors like that are called fancies. When you hear it, I got a fancy diamond, it has to have a very distinctive color. Right?
You were talking about the volcanic explosion at 32 degrees Fahrenheit.
Right.
That was Precambrian era?
Precambrian era of time, yeah, that those explosion pipes mostly occurred. We don't seem to have any explosion pipes like that in the Phanerozoic, which is starting with Crawlobite, going all the way through the dinosaurs. No pipes like that. Okay, this was very early in the history of the Earth, and it was still degassing carbon dioxide. Okay, and when it degassed it, boy, that crack formed, and that came out fast. Other questions? Yeah.
Is the diamond synthesis, is that part of like a nanotechnology?
Well, now they do make nanodiamonds, and these are made by what they call explosion technology, okay? And there they'll take carbon material, and they'll actually put it in an explosion, and it makes nanodiamonds, which are 10 to the minus 12th in diameter. And they make so many of these by explosion technology that they are taken out and sold as grinding and polishing compounds. Okay, so nanodiamonds are still there. We find nanodiamonds in the meteorites that come in that have been part of explosions and supernovas and other forms. So nanodiamonds are almost all detonation diamonds is what the trade name is, detonation diamonds. Yeah?
My question is for the CVD diamond.
Mm-hmm. Carbon, chemically vapor deposited ones. Yeah.
Is it going to stay the same color, red?
No. The chemically vapor deposited ones turn out to be absolutely colorless.
Oh, color.
The colorless. The ones that you make that are the fancies that have all the colors, we were showing those off of another show on the same thing, showing you the diamonds that were made. Those are high pressure, high temperature diamonds, HPHT. Those are made down at the Sarasota labs. Okay? That's Genesis. If you want to go to the website, just type in Genesis. Gorgeous diamonds will appear. Those are engagement diamonds? Yeah, exactly. Right. They'll be orange to red in terms of their fluorescence. Also, they are phosphorescent for a little while, too. When you turn off the light, they still glow for a second. That's called phosphorescence after the energy's gone. Fluorescence means that when you flip the light off, it goes black. But CVD diamonds, okay, they phosphoresce for just a second after you turn the light off. Natural diamonds won't. Another way to tell them apart.
So the ones that give the blue fluorescence are the real diamonds?
Those are the real diamonds. Yep, you stick it under wavelengths, black light, let them sit there, they should fluoresce blue. Okay. If you stick it under there and you get no fluorescence, it's cubic zirconia. And that guy, divorce him. No.
So did you say the fancy ones are more expensive?
Right now, the most expensive diamonds in the world are reds. The Hancock red was the one that we showed you that was, what, 202,000 times greater than its equal weight in gold, right? That was the Hancock red. It was sold per carat. It's been the most expensive sale yet, the Hancock red. Those are out of the Argyle mine. They're all coming from Australia. All coming from Australia.
Speaking of the fluorescence, with the natural diamonds fluorescent blue and the CVD fluorescing the orange pink, is that because of possibly the stress fractures in them, or the way the carbon's arranged, or what causes that?
Actually, I don't know. Okay, De Beers is selling two very expensive machines. One is called Diamond View, and the other one is called Diamond Sure. One costs $10,000, the other costs $50,000. Most jewelers can't buy these machines. So all the big labs have now bought them, right? And those are the machines that do it. And as to why one is fluorescing blue and this fluorescing red, I haven't looked into that, okay, as to what it is, because the arrangement on them is almost identical.
Is the springs the same on them?
Yes. In fact, some of the synthetic diamonds have shown just slightly higher hardness than most natural diamonds. So the synthetics are right in there. Atomic arrangement's the same. Now, they have a different inclusion in them. Remember, we had pyrobe and garnets and chrome dioxide inclusions in natural? Well, to get the carbon to work just right, they have to put in a nickel flux. And sometimes that nickel will actually precipitate directly as a piece of nickel. So when you look in an inclusion in a synthetic high-pressure, high-temperature diamond, you'll see a little metallic inclusion in there, a little piece of nickel. So the inclusions are not natural mantle minerals, right? Because they weren't grown that way in the mantle. Yeah.
For the natural diamond, is there a possibility that they will be depleted, and that's why everybody starts making synthetic?
No. If we've got a couple more slides here, we're going to show you 400 unknown localities in Colorado, Wyoming that haven't even been explored yet. And one of them, right over here on this one, there was a diamond mine at Iron Hill. This is the Kelsey deposit. It ran from 1996 to 2000. It went bankrupt. They had set for the last 2 years, they had set their machine on their mill wrong. It would only collect diamonds that were 8 carats or larger. And so they threw out all the diamonds onto the waste pile. In 2003, people explored their waste pile and were finding 6.2 carat diamonds directly off their waste pile. No wonder they went belly up. How stupid could you get that you misset your mill for 3 years and all the diamonds less than 10 carats went out the window? Right?
I think with the years, I mean, if they were to release all the diamonds they had, diamonds would be...
Yeah, they could flood the cartel. They're a cartel. They could flood it. And diamonds, it's an emotional thing on diamonds, right? You know, when we make these false things, you know, I used to take this into my geology classes as a joke and say, this is the largest diamond. We used to set it up, and I'd say, it's coming from the Smithsonian, and I'd get one of the security guys from campus security to come in and carry it in. And as soon as he came in the door, I'd make arrangements with him just to stand by the door. And they would pass this thing around, and they would have this, and we had talked about it, and the gals, and it would come back, and it would be hot because so many people would hold it so tightly, okay? And not one of them would have looked at it and seen all of this conchoidal fracture, and the angles are wrong, and everything else, and I'd chastise them. And I'd say, it's emotions. Diamonds are emotions. You could see these gals, and they'd go, oh, boy, wouldn't that be something if I could have that on my, okay? And that's what De Beers is counting on. They keep that emotional ploy running, right? So, any other questions? Yeah. Feel free to go. I'll answer questions. We talked for a half an hour before you came, but thank you for coming. Thank you for coming. Yeah.
Fascination.
We could go ahead and shut it off. Bye, folks. Uh-huh.
Given the fact that diamond is not only material, particular atomic array.
Right, there are other materials that have it. But they aren't carbon covalently bonded. That